This demo, we'll be covering the progress we made with the USGS River model. Aside from converting the original model to C in Python, we've changed some of the functionality with the original model along with modifying the GUI. The first significant change to the model takes place in the flow carbon function. In order to simulate a year's worth of carbon flow, the flow carbon function is called enough times to simulate each second's worth of carbon flow within the river. Originally, a single call to flow carbon was equivalent to 5 seconds worth of carbon flowing through the cells of the river. This means that for a single year of simulation, flow carbon would be called roughly 720 times for each hour of 365 days. When we took a closer look at the change of the stock values during a simulation, we found that the rate of change would slow down after a given point. This meant that a lot of cycles spent calling flow carbon were updating stock values by an insignificant amount. To improve this situation, we changed flow carbon to push a minute's worth of carbon. Additionally, we altered the way flow carbon works. The original model would push carbon to all of its adjacent cells. Sometimes, however, the vector calculating how much carbon should be pushed to each cell would be large enough to push cells further than one cell away. The original model ignored this fact and would instead only push to a set amount to its adjacent cells. Now carbon is flowed depending on the vector calculated, so that cells greater than one cell away will have a carbon flowed into them. It was requested that the model be numerically stable and not flow carbon onto land cells, so we performed checks to make sure carbon is only pushed in the cells submerged by the river.
The GUI itself closely resembles the original NetLogo code, but with a few minor changes. The NetLogo GUI used sliders to assign values to biological coefficients. This was done so that the range of values could be specified within the GUI. In other words, it would not be possible to input bad data into the program. The problem is sliders limit the range of values available. This is particularly an issue with precision, where you can only be limited to a few decimal places. We changed this input method to text boxes in order to eliminate this problem, but added hints so that users could be reminded of what values are appropriate.
Once the model finishes running, it spits out an image that looks something like this. This image measures the amount of macrophytes in each 30 by 30 meter cell within the river. To produce this image, the model ran for 5 days using a 50K hydraulic map. As the carbon was moving through each cell in the river, it would alter the macro variable for each cell. Once the model finished running, the C code would build a 2D array of HSV values to pass back to the Python code, which would then create an image using the Python limage library. To compute this appropriate HSV value, we set the hue depending on which stock is selected and the saturation depending on the amount of stock present in a given cell. The value is always set to 1 so that the range of colors will be more apparent. The brown pixels represent the land cells, or any cell not submerged by the river. Unfortunately, the section of the NetLogo code that handled coloring the map contained a lot of magic numbers. Most of these involved specifying the range of values that each stock could take on. For example, Phyto values could range between 0 and 65,000, but there isn't any explanation behind the significance of 65,000 values. Based on responses received from the original authors, these values were chosen arbitrarily to make the resulting images easier to look at. This means that changes we do to the model should technically be changing these max values, but we would need to spend a great deal of time experimenting with this to figure out how they should be normalized. To help alleviate this problem, we output the values from each cell after the model runs. This can allow the values to be viewed and plotted in an Excel file so that appropriate range of values can be selected.
Now that the model is up and running in Python and C, the next task is to calibrate the model to test and improve its accuracy, as well as making the program more interactive overall. Some desired features include being able to select portions of the map and plot different sets of values in real time. This is needed so that anomalies or any interesting section of the map can be further explored and analyzed. It would also reveal patterns that occur over a short period of time, which could provide clues to useful information within the river. Furthermore, images need to be displayed within the graphical user interface. Currently, we can output images at a fixed rate, but did not have time to include them in the graphical user interface. Fortunately, our USGS liaison has expressed a strong interest in continuing the project for next year. This means that these requirements could potentially be homework for a group next semester, so proper documentation of what has already been written will be crucial if we don't want to receive angry emails from disgruntled seniors. The goal is that this model will one day be used to create a generalized carbon model for large river systems that can link ecological models with hydraulic models. There's still a lot of work to be done, but what remains will be a good learning opportunity for future group projects.